Listen to part of a lecture in a physics class.
Have you all turned in your homework? Yes? Good. We need to get started, so let's turn our attention today to vacuums. And no, before any of you comedians ask, I'm not referring to the kind you use to clean your carpets. All right? The vacuums I'd like to discuss are a very different kind. The ones where, well, to put it simply, where gaseous pressure is so low and almost nothing exists. Please pay attention to my wording. Notice I said almost nothing exists, because it's impossible for nothing to exist, so the idea of something being a perfect vacuum is just a concept and not a reality.
Sir, but what about space? I've always been led to believe that space is a perfect vacuum. Isn't that true?
Absolutely not. You might think space is a perfect vacuum, but the fact of the matter is that even deep space isn't one. However, it's as close as we're ever likely to get. You see, space has a lot of radiation, and this causes some pressure to exist, albeit on a minor scale. Also, there's a minute quantity of hydrogen in every part of space. It's not enough to cause friction or to slow down planets and moons in their orbits, but what it does mean is that space isn't empty. Okay, but let's return to discussing the idea of a vacuum before I get totally off track. Historically, philosophers struggled with the notion of a vacuum since they wondered how nothing could exist. Over the centuries, many scientists have contemplated them. Albert Einstein himself considered vacuums worthy of consideration. One of the key concepts of his theory on the speed of light is a value that's measured in a perfect vacuum. Since, as I just told you, a perfect vacuum can't exist, others have suggested that a constant value for the speed of light can't exist either. The book is still out on this, though, and we're not going to concern ourselves with it in this class. It's above what we need to know. That's for my graduate students to ponder instead. So, how do we measure a vacuum? How can we know what the gaseous pressure is? To do this, we use a unit called the torr. That's spelled with 2 R's, by the way. It's named after the Italian physicist Evangelista Torricelli, who's most famous for his work involving the creation of barometers, which measure air pressure. Torricelli theorized that 760 millimeters of mercury was the standard atmospheric pressure on Earth. One part of these 760 millimeters, by that I mean 1/760th, is called a torr. The lower the gaseous pressure goes, meaning that there are fewer torrs, then the closer to a vacuum we get. Vacuums can be classified in several different ways, but we'll look at them from the perspective of atmospheric pressure on Earth, with 760 as the constant. As one gets farther and farther away from Earth's surface, the number of torrs decreases. Finally, in deep space, the torrs become almost immeasurable. However, there's still something there, so even in deep space, as I just said, there's no perfect vacuum. So, what would happen if a person were exposed to a vacuum? If you watch science fiction movies, all sorts of weird things, including people's bodies exploding, happen. In fact, I just saw a movie where an astronaut got a hole in his spacesuit while doing a spacewalk, and his body suddenly exploded. The reasoning is that the pressure of the air in the lungs and the gases in the organs would cause the body to explode because the outside's a vacuum. Fortunately, tests conducted by NASA have proven this notion false. Human skin is actually so strong that the body doesn't rupture.
How did they conduct the test?
Actually, it wasn't so much a test as it was an accident. Back in, I believe it was 1965, NASA was conducting a test in a vacuum chamber here on Earth. An astronaut's spacesuit accidentally sprang a leak, so he was exposed to the vacuum for about 15 seconds before he passed out. The chamber was promptly pumped full of air, so he regained consciousness and, interestingly enough, suffered no long-term effects. So, sure, a person will definitely die if exposed to a vacuum long enough, but at least that person won't have to suffer the indignity of having his or her body explode. So, what are the practical applications of a vacuum? Of course, the vacuum cleaner operates on the principle of suction, which is caused by the creation of a vacuum. Additionally, one of the first and still the most widespread uses of vacuums was, or shall I say is in the creation of light bulbs. The burning filament in the bulb needs a vacuum in order not to burn out rapidly, which is what it would do in an oxygen-rich environment. I'm sure you've all heard of vacuum tubes, right? They were used to conduct electricity in early computers, as well as in early televisions and radar sets.
46. Why does the professor explain the tour? 47. According to the professor, why is there no such thing as a perfect vacuum? 48. Listen again to part of the lecture, then answer the question.
Fortunately, tests conducted by NASA have proven this notion false. Human skin is actually so strong that the body doesn't rupture.
How did they conduct the test?
Actually, it wasn't so much a test as it was an accident.
What does the professor imply when he says this?
Actually, it wasn't so much a test as it was an accident.
49. What is the professor's attitude toward Albert Einstein? 50. How is the discussion organized? 51. What does the professor imply about the class he is teaching? Listen to part of a lecture in a physics class.
Have you all turned in your homework? Yes?